Welcome back to another video on the chemistry mole. Here we're going to have a look at one of the intermolecular forces. So in this particular one we're going to focus on hydrogen bonding. Before you watch this, you really need to have seen the video on electronegativity to understand about the polarity of different molecules. So what I've drawn for you here is a table showing the boiling temperatures of elements bonded to hydrogen in group 6, group 7 and group 5. Now the reason I've started with this is because what we need to do is understand what impact hydrogen bonding has upon the boiling temperature of different molecules. So if you notice here, the first three elements bonded to hydrogen, so we've got oxygen, nitrogen and fluorine, so we've got the NOF elements in the top right hand corner of the periodic table, you can see that their boiling temperatures are significantly higher than the other elements in group 6 that are bonded to hydrogen. So you see a large boiling temperature relative to the others in the group here, a big drop down and then a gradual increase in the boiling temperatures. That's the same when we look at group 6 or group 7 or group 5. So what we need to do is explain the reason for this trend in boiling temperature, this big drop off in boiling temperature. If you've seen the video on electronegativity, you'll understand that the NOF elements, nitrogen, oxygen and fluorine, are the three most electronegative elements in the periodic table. That means that when they're attached to not very electronegative elements, elements with low electronegativity, the molecules are very highly polarized. So if we have a look at some specific examples here, I've got hydrogen fluoride here in the top left hand corner. Now because fluorine is much more electronegative than hydrogen, that has the effect of the fluorine pulling the electrons in that covalent bond towards itself, polarizing the bond here, so you get a delta negative fluorine and a delta positive hydrogen. If two molecules approach each other, the same thing happens in the other molecule, so delta negative here, delta positive here. You've got a difference in polarity, the electrons are spending more time around the fluorines than they are on the hydrogens, and so you get a strong attraction between the hydrogen and the fluorine here, and a hydrogen bond forms between the two. It's as simple as that. That's a drawing that would be acceptable, showing that the hydrogen bond here is 180 degrees. So you see 180 degrees between all the bonds. Let's have a look at another example. So if we have a look at a molecule of water, making sure we draw all the lone pairs of electrons on the oxygen, we get a delta negative oxygen there. That means the delta positive hydrogens must form. So the electrons are spending more time around the oxygen, so they're drawn more towards the oxygen in that covalent bond, creating a relatively strong attraction between the oxygen and the hydrogen. And we have another hydrogen bond here in water molecules. Again, this hydrogen bond here is drawn at 180 degrees between the bond here and the intermolecular force, which is the hydrogen bond here. Have a look at ammonia, bottom left hand corner. So we've got lone pairs of electrons on the nitrogen, delta negative nitrogen here, delta positive hydrogen here, delta negative nitrogen there, and then a delta positive hydrogen here. These hydrogens will also all be delta positive as well, because the electrons are being drawn away from those towards the nitrogen. And then we have a hydrogen bond here that forms between the nitrogen and the hydrogen there. And we just need to make sure that we label that hydrogen bond as well. Now, wherever you see a NOF element, nitrogen, oxygen or fluorine, bonded to a hydrogen, those molecules will generally form a hydrogen bond. So we have a look at the alcohol here. So I've drawn methanol out for you. You can see that a hydrogen bond should be able to form in this molecule because you've got the lone pair of electrons on the oxygens again, delta positive hydrogens, delta negative oxygen, same thing here, delta positive hydrogen, delta negative oxygen with the two lone pairs. And then we've got an attraction between the hydrogen and the oxygen. We've got a hydrogen between two electronegative elements, oxygen and hydrogen here. And therefore, we have a hydrogen bond form here in this alcohol. So in methanol here, we have a hydrogen bond formed. Now, as you start to understand more about intermolecular forces, what you'll also be looking at is the solubility of these different molecules. So the solubility of alcohols in water, for example. So methanol, because it can form hydrogen bonds, it is soluble in water, it has pretty high solubility, because you get the attraction between the hydrogen, the delta positive hydrogen here, and a delta negative oxygen there in the water molecule. Now, as I said, when you understand more about the intermolecular forces here and the interactions of hydrogen bonds, you'll also look at the fact that as the alcohols get larger, when they get more carbons in their chains, their solubility will generally decrease because the larger chains will interrupt these hydrogen bonds. But you'll look at that in more detail when you have a look at some of the organic chemistry. So if we have a look back at our graph here, we can use this to have a look at the impact of hydrogen bonding again. So we've got oxygen bonded to hydrogen here, so we've got the water molecule where we've got a high boiling temperature relative to the other elements in group 6 bonded to hydrogen. So we've got a higher boiling temperature here. Same thing here with hydrogen fluoride in the top left. We've got hydrogen bonding here. And then in ammonia, we've also got hydrogen bonding, so we've got a relatively high boiling temperature for these 3 molecules here. We get a big drop off because the next elements in the group, they don't form hydrogen bonds. The polarity of the hydrogen bonded to these elements is not high enough for a hydrogen bond to form. So you only get a hydrogen bond when you have a NOF element, nitrogen, oxygen, or fluorine. The impact is clear to see here on the boiling temperatures. So hydrogen bonds are the strongest of the 3 intermolecular forces, resulting in a much higher boiling temperature than you'd expect compared to other molecules in their groups. Now, what you'll also be able to see here is that whilst you do get a drop off, you then get an increase in the boiling temperature of these molecules as you go down the group. If you've looked at the video on the induced dipoles, so we're looking at London forces, as you go down the group, the elements that are bonded to the hydrogen have more and more electrons, so the induced dipole-dipole interactions, those London forces, are getting stronger as you get more electrons. So have a look at the video on induced dipole-dipole interactions if you haven't done so already. Thank you very much for watching. Please make sure that you give this video a thumbs up, and if you haven't already, subscribe to the channel.